All right, so the next section is a further section on propositions and logical equivalence, which we'll get to in a sec. So in the last video you saw how to combine some propositions to make new propositions in various ways. For example, you learned and, or, negation, and implication. Okay, so implication we call a conditional proposition. So recall, and I mentioned that that was one of the absolutely most important ones that you'll learn. So a conditional proposition is of the form P implies Q, which recall means if P then Q. And we saw that the truth values of the conditional proposition P implies Q is given by the following table. So P implies Q is true. If P is true and Q is true, it's false if P is true but Q is false. And it's true if the hypothesis is false vacuously. Okay. Our next definition is called a biconditional proposition. And a biconditional proposition is just a proposition, an implication that goes both directions. So in particular, a biconditional proposition is a proposition of the form P if and only if Q. The notation we use to write biconditionals is a double-headed arrow. The truth value of the biconditional P if and only if true, only if Q, depends on the truth values of P and Q in the following way. We need both P implies Q and Q implies P to both be true statements. So both, that's why it's called a biconditional, because both conditional statements, P implies Q and Q implies P, both need to be true. Some terminology that you may encounter P if Q, this means if Q then P. Or in our notation, Q implies P. In this setting, we say Q is a sufficient condition for P. There's a lot of terminology, so I just want to make sure you've heard all of the words so that you're not surprised by anything. Another one is P only if Q. This means if P then Q. And of course we write this, P implies Q. In this setting, we say Q is a necessary condition for P. So the truth value of the biconditional P if and only if Q can be described by the following table. I want to show you it in comparison with the implications P implies Q and Q implies P, so you can see that it is in fact only true when both are true. So P implies Q is true when Q is true and P is true, and when P is false, but it's false when P is false, it's false when P is true and Q is false. Q implies P is only false when Q is true, but P is false. And the biconditional is true when both conditionals are true. It's not true if one of the conditionals is true and the other one is false. But we see that in this last case, we also have both conditionals are true, so we get a true here. So that means that the biconditional is true if both P and Q are true, or if both P and Q are false, but not if they have different truth values. So biconditionals are true when P and Q have the same truth value. One observation I want to make is that definitions, whenever something is defined to be a certain thing, definitions are always if and only if statements, even when they're not explicitly stated that way. Okay. So now I'll give you the definition of the term logically equivalent. So logically equivalent propositions, when two propositions have the exact same truth values, regardless of P and Q, so depending on the logical values of P and Q, then we call them logically equivalent. So let me be a little more specific about that. So when two propositions have the same truth values, for any choice of truth values for the P, Q, R, whatever is inside comprising the proposition, then they're called logically equivalent. The notation we use for this is 3 horizontal lines. So we write P is equivalent to Q, that's how we read this, whenever P and Q are two propositions that have the same truth values for any choice of truth values for their components. So one of the absolute best examples that you will see over and over and over again are called De Morgan's laws. when we talk about sets in the next unit, we'll also talk about De Morgan's laws of sets later. So for now, I'll call these the De Morgan's laws of logic. Okay, so there's two of them. One of them says if we take the negation of the proposition P and Q, that this is logically equivalent to the negation of the proposition P or the negation of the proposition Q. The other one is similar but different because we swapped these ands and ors. So the second one says the negation of the proposition P or Q is logically equivalent to the negation of P and the negation of Q. Okay. So pause for a second and see if you can figure out the truth table that shows these equivalences. Okay, so we want to show a truth table that demonstrates these equivalences. So let's look at the second one here. So we want to consider P, Q, and we want to compare the two sides. So we want to look at P or Q, so not P or Q. And we also want to compare with not P and not Q. And since I don't have a lot of room, I'm going to skip the intermediate steps here. So we could have true, 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 false, false, true, or false, false for our truth values of P and Q. P or Q is going to be true whenever either P or Q is true. So the only situation where it's going to be false is down here in the last row. Since we're taking the negation, that's the only situation where this will be true. The rest will all be false, because in all three of these situations, P or Q is true, so not P or Q is false. Now, here we want to take the and of not P and not Q. Well, this is only going to be true if not P and not Q are both true, which means it's only going to be true if P and Q are both false. In all the other situations, one or the other is false. In this case, both. In this case, P is false, not P is false. In this case, not Q is false. So another way of visually understanding logical equivalence is two propositions are logically equivalent if they have the exact same column in a truth table. So here we see that these columns match row for row. So logical equivalence means no matter what row we're in, no matter what combination of truth values of the propositions that comprise the propositions we're looking at, we will always have the same truth values. Next example, what do you think the negation should be of the implication P implies Q? So try to figure out a logically equivalent statement for the negation of P implies Q using our truth table. Okay, let's see how you did. So the claim that I'll try to demonstrate for you is that the negation of P implies Q is logically equivalent to P and not Q. So we can demonstrate this using a truth table. So if we look at possible values of P and Q, it's either true, 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 false, false, true, or false, false. And now we look at the implication P implies Q. We can negate that, that's what we're interested in. And we want to see if that column is the same as the column P and not Q. Okay, well we've already seen what the column for P implies Q is. We know it's only false if P is true and Q is false. That's the second row here. In all other cases it's true. In these bottom two cases it's true vacuously. So now we just have to reverse this to form the column not P implies Q. So in this case, the only time it's true is row 2, and then every other row is false. Now let's think about P and not Q. P and not Q is going to be true only when both P and not Q are true. Well, that's only going to happen when P is true and Q is false. So when P is true and Q is false, that's the second row, we'll get a true value here. If either P is false or not Q is false, we'll get a false. So P is false in these two, so we get false down here. Not Q is false when Q is true, so we get a false in this first row. Now if we compare columns, we see that these two have the exact same columns in the truth table, and so we have this logical equivalence. Okay. As an example in words, we could look at the example where P is the proposition Sam gets drafted. And Q is the proposition Sam will play in the NBA. So the proposition P implies Q is the proposition if Sam gets drafted, then he'll play for the NBA, right? What is the negation of that proposition in words? So pause for a second, see if you can figure that out. So the negation, as we can see over here, should be P and not Q, right? So that would mean Sam gets drafted and Sam does not play for the NBA. So this in words is the logical negation of the conditional statement P implies Q. Okay, so we have two more definitions and from this section, and they're very, very important ones, because we're going to use them heavily, in this terminology heavily, in our next unit on proofs and induction. So the definition is based off of the conditional proposition P implies Q. So given a conditional proposition, we define the converse of that proposition and that's the proposition Q implies P. And the other terminology is the word contrapositive. The contrapositive of the conditional proposition P implies Q is the proposition not Q implies not P. Okay. Now, one thing I want you to check right now is whether or not a proposition and its converse are logically equivalent, and whether or not a proposition and its contrapositive are logically equivalent using a truth table. Okay, so you were supposed to check whether a conditional proposition and its converse or a conditional proposition and its contrapositive are logically equivalent or not using a truth table. So let's check. So let's look at P, Q, P implies Q, Q implies P, and not Q implies not P. So we know that P implies Q is only false if P is false, or sorry, P is true and Q is false. All the other times it's true. Same goes for Q implies P. It's only false if Q is true and P is false. So that's this third row, and in all the other cases it's true. So we see immediately that these two columns are not the same, so these are not logically equivalent. These are very different statements. Now if we look at not Q implies not P, we know the only way this can be false is if we have not Q as true and not P as false. Of course that corresponds to Q being false and P being true. I think I just said that wrong. The only way this conditional statement is false is if not Q is true and not P is false, which means Q is false and P is true. In all other cases, we have that the proposition or the conditional proposition is true. Okay. So now we see that looking at columns, the column for the original conditional proposition P implies Q is completely matching the contrapositive of the proposition not Q implies not P. So this is, contrapositive is logically equivalent to P implies Q. One example in words is the following. If it's raining, then it's wet. This is a classical example of an if P then Q statement. If it's raining, then it's wet. Q implies P, if it's wet, then it's raining, is not true, right? Although if it's raining, then it's wet is true. However, if it's not wet, then it's not raining, is the same as saying if it's raining, then it's wet. Cool. You can think about it a little bit, but it's a good example. All right, and so that will conclude the second video.